Hey all, in this AP Computer Science A video, we're going to cover Unit 2 using objects. If you don't like the pace of the video, adjust the playback speed in YouTube. Check the timestamps to jump to specific topics and check the video description for other resources. In this video, we'll learn how primitive types are different than object types in Java and why it matters. You've probably already learned that there are 8 primitive types in Java. Primitive types are small, simple pieces of data. As an example, we create a primitive variable int a and initialize it to 3. The value for a is stored in the stack part of memory. The same thing happens when we create a double variable and a Boolean variable. Now let's create an object type variable. Object types can also be called reference types. Some common object data types you may have heard of are string, array, and scanner. Dog is an object type that I've created. Unlike primitive types, you can design your own object types. This is a common way to declare and initialize an object type variable. Primitive type variables have a value stored on the stack. Object type variables also have a value on the stack, but for object types, the value is a pointer. The pointer points at a place in heap memory where the object is stored. Heap memory is larger than stack memory, so it can hold objects which are more complex than primitive types. Let's create another object type. The objects themselves are completely equivalent, but they have different identities because they each exist in a unique part of the heap. The two pointers are not equivalent because they point to different places on the heap. Now let's declare a new primitive variable d and assign it the value of a. D is created and we copy the stack's value for A and assign it to D. For data on the stack, we don't think about the identity because each variable has its own unique value. Now let's create a new dog type variable Z and assign it the value of Y. Z is created and we copy the stack's value for Y and assign it to Z. Notice that we copied the pointer, not the object. When we set one variable equal to another variable, we always copy the data on the stack. But Z's pointer and Y's pointer have the same value because they are pointing at the same location on the heap. X's pointer has a different value because it's pointing to a different location on the heap. Now let's learn why these differences are important. Look at these 3 lines of code. Here, we're using double equals, which is the equality operator, to compare A and B. In Java, the equality operator compares the value on the stack for 2 variables. Even though A and B are different data types, Java recognizes they are mathematically equivalent and will evaluate to true. Next, we compare X and Y. The stack data for X and Y is their pointers. The pointers refer to different locations on the heap, so they are not equivalent, and this expression evaluates to false. There are ways to check whether the objects X and Y are pointing at are equivalent. In this case, they are. However, the proper way to compare objects depends on the object type and is never double equals. Finally, we compare Y and Z. Y and Z's pointers have the same value because they are pointing at the same location on the heap. This expression evaluates to true. Let's look at some other situations. Suppose we change the value of the primitive d to 6. It's fairly straightforward to see what happened. And now, if we use the equality operator to compare A and D, it would evaluate to false. Now, with object types, there's 2 types of changes we need to consider. First, we can instruct the object that Y is pointing at to change to blue. For now, don't worry about how we did that, just accept that it happened. The change affects both Y and Z because they are both pointing at the same object. For a different type of change, we can instruct the Z variable to point at a different object. This doesn't affect Y at all because Y is still pointing at the original object. Whenever you are modifying object types, you need to consider, are you modifying the object itself? Or are you modifying where the variable is pointing? In this Java tutorial, you'll learn about using classes and creating objects. By the way, an object is also called an instance of a class or an instance. First, let's talk about what an object is. In object-oriented programming languages, like Java, objects have two types of characteristics. First, they have states, which in Java we represent with field variables. Second, they have behaviors that in Java we represent with methods. Imagine a light bulb object. Two states might be color and size. Three behaviors might be flash, turn off, and switch color. Let's create a light bulb object. This object has the value yellow for the color field and the value 5 for the size field. If we call the flash method, it causes the object to behave in a certain way. Now let's call the switch color method. You can see that the switch color method changed the value of the color field. It's very common for programmers to write methods to modify the values of fields. Your next question might be, where did the code for the object come from? The answer is from a class. A class is like a blueprint or a template for an object. There are a number of classes built into Java, so often we just use those pre-made classes. Some examples of pre-made classes are the string class, arrays class, and scanner class. You've probably used at least one of these already. Sometimes programmers write their own classes. Regardless, once you have a class, you can use it to create as many objects as you want. Anyway, now that we've covered classes and objects conceptually, let's learn how to create objects with code. Here's how we can create an object for the lightbulb class. We start by stating the name of the class, in this case lightbulb, then a variable, in this case x, followed by equals, new, lightbulb, open close parentheses, semicolon. What we did is create a variable called x of type lightbulb and told it to point at a newly created lightbulb object. Now, let's look at another way to declare and initialize a lightbulb object. On this line, we create a lightbulb variable y. On the next line, we create the lightbulb object and tell y to point at that object. We're doing the same thing, but in the second example, we split up the steps. We can't access an object directly, so we need a variable to allow us to identify the object. It's like how people need names so we can identify them. Let's look at a third example. Here we declared a variable z and initialized it with a new lightbulb object. But you'll also see an additional piece of data. Anything inside the parentheses gets passed to the constructor and is used in the creation of the object. In this case, I pass the string green to the constructor, which caused the lightbulb's color field to be set to green. Now, you can't just pass anything you want to a class's constructor. The programmer of the lightbulb class determined what type of data the constructor could accept. When working with a class, you need to know what type of arguments you can pass to the constructor when making a new object. Next, let's talk more about fields. We learned earlier that in Java, an object's states are managed by field variables. There are two types of fields you need to know about. The first are called class variables because they belong to the class. These are also known as static fields. The second are called instance variables because they belong to the individual instances. These are also called non-static fields. Let's pull up the lightbulb class and some lightbulb instances again. The lightbulb class defines color as an instance variable. That means each instance has its own unique copy of the variable. When we change the value of color for the instance that y is pointing at, it only affects that one instance. Size is defined as a class variable. It belongs to the class and is shared by all instances of the class. When we change the value of a class variable, it affects the class and all instances of the class. When coding a class, the programmer decides which fields are class variables and which are instance variables. Next, let's look at methods again. There are two types of methods, static and non-static methods. First, static methods can be called from either the class or an object, while non-static methods can only be called from an object. To understand better, let's look at two different methods in the lightbulb class. The decrease size method is static, and the switch color method is non-static. Let's write some code to see how we can access the methods. Lightbulb.decreaseSize. Decrease size is static. It's a behavior of the class, so we can call it from the class itself. There doesn't even need to be an object in existence for us to call this method. Alternatively, we can create an instance of the lightbulb class, It's legal to call static method decrease size from the variable q because an object always has a class standing behind it. However, this could be confusing to other programmers reading our code. You should make a practice of calling static methods from the class itself like above. Switch color is a non-static method, so we must call it from an object. The only variable we have that is pointing at a light bulb object is q, so we'll call it from q. As a non-static method, an object behavior, switch color, cannot be called from the lightbulb class. This line of code will give the error, non-static method cannot be referenced from a static context. The final thing to know is that static methods can only access class variables which are properties of the class. Conversely, non-static methods can access class variables, properties of the class, and instance variables, properties of the object. This is why the switch color method had to be non-static, so it could access and change the instance variable color. This fact will be important when you learn about writing classes in a later lesson. Before we end, I wanted to mention that there are a few classes that have unique ways of creating objects. Some examples include the string class and the array class. Don't worry about those now, but be aware that exceptions exist. In this lesson, we'll learn about calling methods in Java. Some important points. In object-oriented programming, we can think of methods as behaviors. Static methods are behaviors that belong to the class, so we call the methods from the class itself. A class is like a blueprint for an object. Non-static methods are behaviors that belong to objects. We need to use the class to create one or more objects. Then we call the non-static methods from a specific object. Let's look at this cake class. As discussed earlier, we can think of a class as akin to a blueprint. You might expect the cake class to have fields and constructors, but we aren't displaying them. If you don't know what fields and constructors are yet, that's fine. We only see the method headers. The method bodies don't matter to us because we don't care how these methods do what they do. Think of it like a car. We don't need to understand how a car works to drive it. Let's look at the method headers and learn what information we can from them. Public is an access modifier. This means we can call the method from either inside the cake class or from another class. Compare that to the private access modifier, meaning the other method can only be called from inside the cake class. Next, the static keyword tells us this behavior belongs to the class itself. We don't actually need to make a cake to call list flavor choices. We can call the behavior from the cake's blueprint. Compare that to how many calories, which doesn't have the word static. As a non-static method, it must be called from a cake object. Different cake objects will have different numbers of calories, so it makes sense that this will be a non-static method. When I say that different cakes may have different numbers of calories, this variability is key to understanding why how many calories is a non-static method. Since each cake object could have different ingredients, the number of calories will vary from one object to another. That's why the method needs to be called on a specific cake object, allowing us to calculate the calorie content based on the unique characteristics of that individual cake. This is our return type. It tells us that every time list flavor choices is called, it will send back a piece of string data. In the case of this method, we can surmise from the name that the returned string will be a list of the different flavors of cake objects that can be created from this class. Return types can be primitive or object types. The how many calories method will return a piece of data of int type. Add writing has a void return type, meaning it will not return any data when called. Here is the method name. It should be in lower camel case and describe what the method does. Finally, we have the parentheses, which can hold one or more parameters. Parameters are variables that receive data when we call the method. List flavor choices doesn't have any parameters. Compare that to add writing, which has one string parameter. Every time we call add writing, we need to pass it a string which will populate the words variable. New programmers often confuse return types and parameters. Remember, parameters tell you what data needs to be sent to a method when we call it. Return types tell you what type of data will be returned back. Now let's look at the bakery class. We'll write some code in the main method of the bakery class. The main method is automatically called when we run a class. For reference, I've included the method headers from the cake class. Suppose we attempted to call list flavor choices. While this is a valid method name in the cake class, there is no method by this name in the bakery class, so Java can't find it. Let's look at the cake methods and learn how to call them from the bakery class. List flavor choices is a static method, which means it's a behavior that belongs to the cake class itself. To properly call it from another class, we will say cake.listFlavorChoices, which will run without error. Let's go back and look at the return type of the method. It returns a string. We aren't doing anything with the return data, so the list of flavor choices will disappear into the ether. Let's print out the return string. Next, let's call the HowManyCalories method. This method is non-static, so it's a behavior that belongs to the individual objects. To call it, we need to create at least one object. We start by creating a variable of type cake and name it vanilla. Since vanilla is a variable of an object type, we will have to have it point at something before we use it. Here, we create a new cake object and have the vanilla variable point to it. In memory, we have the vanilla variable, which points at a cake object. The cake object is an actual cake that we can do things with. Contrast that to the cake class, which is just a blueprint for a cake. We can make as many cake objects as we want. Different cake objects may not be identical, but they must all follow the specifications created by the class blueprint. HowManyCalories has an int return type. That means the method will return the number of calories in a particular cake as an int. Again, we are just letting that data disappear into the ether. Instead of printing it out like before, let's store the data in a variable called calories. Next, we want to call the addWriting method. It is a non-static method, so we must call the behavior from an object. It has a void return type, so no data is returned. The addWriting method has a string parameter. That means when we call addWriting, we need to pass a string argument. The argument we pass will populate the words parameter, affecting how the addWriting method behaves. When we call the addWriting method, it modifies the object. Some methods modify objects while others don't. Finally, let's look at the mixIngredients method. This method has a private access modifier, meaning it can only be called from inside the cake class. There is no way for us to directly call mixIngredients from the bakery class. However, if one of the public methods we called happens to call the mixIngredients method as part of its workings, we would have indirectly called mixIngredients. Before we wrap up, let's quickly recap what we've covered in this lesson. We learned that methods in Java can be thought of as behaviors, with static methods belonging to the class itself and non-static methods belonging to the individual objects. We explored how static methods, like list flavor choices, can be called directly from the class, while non-static methods, like HowManyCalories, require an object to be created first. We also discussed method headers, including access modifiers, return types, method names, and parameters, and how they tell us important information about what a method does and how to use it. Welcome. In this Java tutorial, we'll learn how to use the string class. Some important facts to know. String is a data type that holds text. Internally, strings are an array of the primitive type char. The string class has a variety of methods to compare and modify strings. We'll start by looking at the most common way to declare and initialize a string, which is to say string, the name of the variable, in this case, a, and then set it to a string literal, in this case, hello. Java will place the variable on the stack and create a pointer pointing to the object on the heap. Typically, it will put it inside the string pool. This means if we create another string variable with the same value, Java will look in the string pool, see it's already there, and then have the new variable point at the same memory location. This behavior reduces memory usage. This behavior is different from most other object types in Java. Now let's look at a less common way to declare and initialize a string variable. This is how we declare and initialize most objects. When we do it this way, Java will create a unique object outside of the string pool. If we do it again this way, even if it's the same value, it will create a second object on a different part of the heap. While this is unusual behavior for a string, this is typical for most objects. Now let's look at this line of code. For this lesson, SOP stands for System Out Print Line. A double equals B checks if the variables have the same data stored on the stack. For primitive types like int or boolean, double equals works well because all of the data is stored on the stack. However, with object types like strings, double equals checks if the pointers on the stack are pointing at the same location on the heap. In this case, A and B point to the same memory location, so it will evaluate to true. Now let's look at another line of code. We're checking if C and D are pointing at the same memory location on the heap. They aren't, so even though the data itself is the same, it will evaluate to false because the variables point at objects in different physical locations. These two objects, while equivalent, have different identities. Checking if two variables are pointing at the same memory location is called referential equality, and is why double equals isn't a good way to compare objects. In the case of strings, it will generally work, but it is a risky practice. For strings, we compare equality using the equals method. So A equals B compares the data that A and B point to. In this case, A and B are pointing at the same block of data, so they will, of course, be equal. C and D are pointing to different memory locations, but the data in those memory locations is the same, so the equals method will return true. Let's look at another way to use the string class's equals method. Here, we're calling the equals method from the string object that A is pointing at. We're passing the string literal hello to the method. Since A is pointing at a string object that is equal to the string literal we're passing, the method will return true. Next, let's change A. This created a new object in the string pool and changed A to point at that new object. The original object is unchanged. We didn't modify the object, we created a brand new object and changed where A was pointing. In fact, unlike most objects, strings are immutable. That means once they are created on the heap, they can't be modified. People often get confused because it seems we have modified the string A is pointing at, but really, we just created a new string. Let's look at some other examples to see how strings are handled in memory. We created the E variable on the stack and have it point to a new object in the string pool. Next, we create a new variable F and copy the data from E. In the case of a primitive data type, we would copy the actual value. For object types like string, we copy the pointer so both variables are pointing at the same object in heap memory. This would happen even if the string weren't in the string pool. Next, we create a variable G on the stack and have it point at a new object in the string pool. Finally, we create a fourth variable H and have it point at a newly created object, capital HI, on the heap. Now let's look at some comparisons. E equals F checks if the two variables point at objects with the same value. E and F point at the same object, so naturally that object has the same value as itself, and the method returns true. Next, we check E equals H. Even though E and H both point at objects that say hi, the strings equals method is case sensitive, so it returns false. Finally, we use the equals ignore case method to compare E and H. Ignoring the capitalization, E and H point at objects with the same value, so the equals ignore case method returns true. It's important to know that even though all object types have an equals method, many objects equals method only checks referential equality, so their equals method behaves like double equals. Now, let's look at some other useful methods in the string class. Here we call the length method. The length method counts the number of characters in the string and returns it as an int. G is pointing to howdy, so length will return 5. Next, we have the substring method, which copies a part of the string and returns that part as a new string. The original string the variable is pointing at will be unchanged. We saw that when calculating a string's length, we start counting at 1. But when using the substring method, we start counting at 0. For a string with length 5, the indexes go from 0 to 4. In this example, we passed one argument to the substring method. The substring method will start at index 2 inclusive and go to the end of the original string. This call returns the substring wdy. There's another version of the substring method with 2 parameters, so we provide it with 2 arguments. In this case, the first argument is where we want to start, and the second one is where we want to stop. However, you must be careful because the first value is inclusive while the second one is exclusive. We start at index 1, but we'll end 1 before index 4. This call returns the substring OWD. Let's look at the compare_to method. The compare_to method in the string class compares the two strings lexigraphically and returns an int of their difference. If the two strings have the same value, it will return 0. In this case, it returns -32. If we switch the order of H and E, it would return +32. Finally, let's look at a couple of examples of how we might use these methods. Here, we're taking the length of the string H is pointing at and storing it in an int value I. Notice that since I is a primitive type, all the data is on the stack. Here, we check if E equals the string literal pi. In this case, it returns false, so the code in the curly brackets doesn't get executed. The string class has many other useful methods you can read about in the documentation linked in the video description. In this lesson, we'll learn about the 2 uses for the plus sign in Java. Some important facts to know. The plus sign in Java has 2 functions. First, mathematical addition. Second, concatenation, which takes 2 strings and combines them into one longer string. In some cases, Java will automatically convert different data types to allow them to be combined. These rules are Java-specific and may differ in other languages. Let's take a look at this expression, 3 plus 5. We're adding 2 ints, so it's going to evaluate to the int 8. Now let's look at 2.0 plus 4.0. These are doubles, so it's going to evaluate to the double 6.0. In this example, we're adding the double 4.2 and the int 3. To avoid loss of precision, Java automatically converts the int to a double, and we're going to end up with a double 7.2. Here's an example of how we might use the original expression in a full line of code. Double A equals 4.2 plus 3. Now we're going to look at a different operation, string concatenation. Many languages like Java also use the plus sign for concatenation. Here's an example of using the plus symbol with 2 strings. Java combines these 2 strings into a longer string. Hi there. Now let's look at this expression. The first operand is a string and the second operand is an int. Java recognizes that it can't perform addition here, so it implicitly converts the int 8 to a string. Now it concatenates the 2 strings into the string great. Here's an example that shows the importance of operator precedence. The plus operator is left associative, so we'll execute from left to right. 8 plus 9 is 17. 17 is implicitly converted to a string, and the 2 strings are concatenated into the string 17 years old. In this variation, we add a set of parentheses. Parentheses have the highest precedence, so we start with the second plus symbol. The 9 is implicitly converted to a string and concatenated with the second string. Next, 8 is implicitly converted to a string and concatenated into the string 89 years old. In this lesson, we're going to learn about the math class in Java. Some important facts to know. The math class in Java contains methods that perform various mathematical functions. All methods in the math class are static, so we can call methods directly from the class. For example, math.random. You can't extend or create an instance of the math class. Math ABS. This method calculates the absolute value of a number. We can pass the ABS method an int, a double, a float, or a long. The ABS method will always return the same data type as what it was passed. Here's an example. If we pass math ABS the double -3.2, it will return the double 3.2. Math POW. This method calculates exponents. For example, 5 to the 4th power. Math POW can be passed a combination of 2 ints, doubles, floats, or longs. Math POW always returns a double. For example, if we pass the int 3 and the double 2.0, it calculates 3 to the second power and will return 9.0. Math square root. This method calculates the square root. The square root method can be passed an int, a double, a float, or a long. Math square root will always return a double. For example, if we call math square root and pass it the int 9, it will return the double 3.0. Math pi. Notice that there are no parentheses after pi. Unlike the previous examples, which were methods, pi is a public field variable that we are accessing from the math class. Most field variables we use are private, so we can't access them this way from outside the class. Math pi is a double variable that is approximately equal to the mathematical constant pi. For example, we might use it in the expression circumference equals 2 times math pi times radius. There are a variety of other useful methods in the math class. To see them all, go to a search engine, type in Java, the current version number of Java, and math. You will find a document detailing the math class, including all the methods and their variations, what type of data we can pass to the methods, and what type of data the methods will return. You've reached the end, and if you have a test coming up, good luck. Tell me in the comments if there was something in the video that you found useful. Check out the other resources in the video description and on the channel, and I'll see you soon.